Good afternoon, everybody. My name is Antonio Castello. I'm Technology Manager at Epic, and it's a pleasure to be here today, September 15, with another of our online technology meeting series. And this time we are going to talk about new developments for spectroscopy sensing and monitoring on the mid-infrared regime. So we were chatting a little bit before the official start of the meeting that is a topic that sometimes we cover in other topics. So we have presentations for bio and medical applications in some cases, also, of course, in our defense meeting. But I thought it's interesting also to have a specific meeting to discuss about what is new regarding mid-infrared solutions, mid-infrared spectrometers. That is something that I'm particularly interested and also understand what's new in terms of developments, but also emission, also detection, photodetectors for sensing and monitoring. So I think we are going to have a really nice ASO presentation today with a lot of interesting information. And for the ones that are new, so this is Epic. Epic is a consortium of more than 100 companies that are together because they want to grow together and develop the photonics business in Europe. Our goal and as Epic staff is to support them and help them to find new opportunities of collaboration, new business opportunities as well, to understand about what's happening in different new applications or markets. So in case you are interested in knowing more and you are not inside our consortium, please feel free to come back to us and we can give you a little bit more information about what is Epic about. Just as a bullet points, we help our members with access to market reports. We have an agreement with specific companies like Tematis or Joel that develop market reports in different topics. So you will have, in some cases, free access to these market reports, in some cases, special conditions. That is a good way to understand about new markets on trends for the future. We also support with human resources. We have a Job in Photonics website for those of you who has open positions and they want to promote. We do LinkedIn posts and talk in social media about open position in our members. Also with investment, we connect companies with investors or companies that want to buy other smaller companies. We connect together so they can increase also their portfolio. And then also with networking and technology discussions, that is the task of us as a technical managers, supporting any technological request that you may have, technical issue, technical interest, or if you are looking for some component that you don't find, and also in organizing meetings on site and online so you can find with the networking opportunities, companies for collaboration and partnership. And I would like to encourage you to go our website because, as I mentioned, we organize a lot of activities during the year. This is a small summary of what's coming. Regarding on-site meetings, we are going to visit India in one of our delegation trip, where we will visit Lazy World of Photonics India with some members, and we will help them also to explore the market there. In some cases, find distributors in the country. That is a point of interest for several of our members, and also see how is the business in this country. This one is really soon, but we will have more delegation trips in the near future. So I encourage you to check what's happening. And our director, Carlos Lee, he's the one organizing, and you can share any doubt or any concern about these delegation trips. And of course, we will be present in the next exhibition, so W3 Fair in Jena. So we will have a VIP breakfast and also a panel discussion in this show. And of course, ECOC in Copenhagen, where we will have a lot of activities, a VIP reception, some activities related with careers and human resources with young people. So if you are interested in hiring young students and young workers, it can be a good opportunity. And we will have also a tech watch during the show to talk about technology. And we will combine with a specific Epic technology meeting at the NKT Photonics facilities in Birkerot to talk about photonics for quantum technologies. So if you are interested in the quantum world, I also encourage you to check the agenda to October 2nd after ECOC. So it could be a good opportunity if you attend the show combining with our Epic meeting. And regarding online, we will continue doing online technology meetings in different topics. So you will see photonics for metrology systems, material for photonics chips, Also, pay attention to the October 21, which is the day of photonics, and we offer the possibility of doing different activities to promote the photonics in the industry. So you can contact my colleagues to see what can be done in terms of marketing or announcements to take advantage of all the visibility that we give to the day. Also, we will continue with the sustainability work group. In this case on standards, and I will want to also to keep an eye on October 27th because we will have online technology meeting on photonics for defense, in this case, active and passive imaging systems. So we will have presentations of different companies offering imaging solutions for defense. So with infrared, I'm sure several of you are interested in attending. And also regarding a couple of meetings that I will moderate in the next months, one related with photonics and photonics for bio and life science, photonics for cancer, pathology and therapy, and surgery. With, as I mentioned, near mid-infrared is also interesting in some cases, both for illumination and detection of different biological samples. And regarding the meeting today, this is the slide that we normally prepare in our online meetings, showing all the companies registered. So it's good to have this great distribution of equipment manufacturers, company developing also components and modules, companies doing metrology and testing solutions, and also end users or integrators from different fields. So oil and gas, we have steel, defense, medical, food industry. So we see that the interest in mid-infrared technologies is quite broad. So I hope with all these developments, you will find an interesting partner, and also in the future, we can discuss about this kind of opportunities and how can we help from EPIC to promote in these fields. And we want to also say thank you to our sponsor today, Hamamatsu. Most of you know Hamamatsu. They cannot be here today, but they asked me to present this slide showing the different solutions that they can offer in the broad range of wavelengths from UV to infrared components, optical elements, sensors, and the compact spectrometers that are showing in this slide. So feel free to contact me if you are interested in discussing with them about any of these solutions. And I'm reaching the end of my welcoming words. So as I mentioned, we have several presentations in different topics, rating components, emitters, also detectors. And I hope all of you will be interested. After the presentation, we will have time for Q&A. So I encourage you to raise your hand and ask the question directly, switch on your camera, your question directly to the speaker. And I hope you have a nice discussion. We have a nice discussion this afternoon. Afterwards, most of the presentation will be uploaded in our website, but also feel free to contact me in case of any particular point that you want to discuss with one of the speakers, and they will be happy to chat with you more in private. So nothing else from my side. So it's a pleasure to introduce this moment Andreas Theodosiou. He's the CEO of the company Lumoscribe in Cyprus. It's a quite exotic, let's say, location. We don't have many members in Cyprus, but it's great to have Andreas today here with us. They are offering different solutions and focusing grading components for sensors and fiber lasers. So, Andreas, the floor is yours, so you can share your screen and start your presentation.
Thank you, Antonio. Yeah. So, can you see my screen?
Yes, we can.
So, first of all, thank you for the invitation to present here today some of the tasks that we work in our company. As Antonio said, my name is Andreas Theodosiou. I am the founder, the director of the company Lumoscribe, and today I will try to present briefly some of the grading components that we are developing for sensors and fiber lasers for wavelengths beyond 2 microns. So I will take the opportunity to say a few words about Lumoscribe. As Antonio said, we are in the Cyprus. We are established in May 2018, so we are 7.5 almost years old. We are a small company of 6 people, including research and administration staff, which is specialized for the development of components in optical fibers, either for sensing or for laser applications. So we are a company which is growing organically, mostly through different national and private research projects, either from the local funding body or from the European funding agency. So one of the main concepts that we are interested as a company and we are working the last, let's say, 6 years is the mid-IR fiber lasers. And here we are defining the mid-IR region with the broader definition, let's say starting for around 2 up to 20. Because why? Because for different reasons, very exciting application in many fields, gas sensing, biomedical, material processing, and so on and so forth. But as you possibly know, or most of you in the audience, these wavelengths are quite beyond the operational wavelength range of silica fibers. So different kind of materials, other materials, more exotic, let's say, should be used, like fluoride fibers and chalcogenide and some other kinds of materials. So as a result, these materials are quite different in terms of optical, chemical, and mechanical characteristics. And especially when you are talking about monolithic fiber lasers, all the modifications that need to be performed to develop the component need to be highly precise to have usable components with the minimum losses. Need to mention here that with the monolithic term, we mean that the whole fiber laser, it is completely not using free space components, but all the components are inside the fibers. So starting with some components in silica fibers, using silica fibers, we develop high reflection gratings in thulium and holmium silica fibers. Here you can see some spectrum of the high reflectivity gratings and some chair gratings over there with a low reflectivity in order to create the fiber laser cavity. And when you characterize these fibers in fiber laser configuration, we found something like more than 64% of slope efficiency for the thulium fiber lasers, and around 72% for the holmium fiber lasers, which when you compare these values with designs which were developed with gratings in passive fiber spliced with the active, we are talking about an improvement of around 50%. Need to mention here that these lasers was only dedicated for low to medium continuous wave fiber lasers. So on the same way, we proceed to more exotic, let's say, fibers, fluoride, indium fluoride, and Ziplan fibers. So we successfully create some high reflectivity gratings, fiber gratings in double cladding fibers and single cladding. And we develop a mid-IR fiber laser at 3.5 in collaboration with Mirage Photonics, Cyprus University of Technology, and the University of Adelaide in Australia, using a double cladding erbium dome fiber laser with a laser emission at almost 3.5, precisely 3.466 around nanometers. And it is a hybrid, let's say, design. So one reflector grating and the other is mirror, and it was pumped with a dual wavelength pumping method. And as you can see from the results, very nice laser lines and a slope efficiency of around 50.2%, which it is almost double when you compare the same cavity using exclusively free space components. So this laser was used to measure acetone vapor sensing for this kind of application. So it was a simple setup, as you can see here, a reference arm, and the measuring arm. We have a chopper that will create these sine waves and compare using oscilloscope the difference between the two arms. So we achieve with this setup something like 1200 ppm per percentage for a single pass laser. But of course, this sensitivity can be significantly increased either by multi passes of the laser or by tuning the laser to a lower wavelength, which is matching better to higher absorption, as we can see here in the figure of the NIST data. Another type of grading that we developed recently, it's long period gradings using Zipline fibers. So basically there are two, you can categorize this kind of gradings in two types according to the manufacturing process. So the first one, to make refractive index modification in the core of the fiber. And the second one is to, and the second one is to mechanically induce some deformation, periodic deformation of the cladding at the core of the fiber. So the periodic, these structures satisfies the long period equation, and the light is matching to specific cladding modes. So using a filament process and splicer, we very well control the dimension, the diameter of the waist and the diameter. So we were able to have a control, let's say, periodic structure of minimum around 180 microns. And as you can see from the figure here, it is very consistent as a methodology. So for each period, we have a constantly 3 to 4 dB increase in the spectrum per period. So this setup was characterized in terms of loss, and we end up something like less than 0.8 dB. And this is very useful as application in fiber laser, but also for sensing, because especially the second method, when controlling the waist diameter of this component, basically the light in the core of the fiber having higher access to the ambient refractive index, and can be very useful for liquid sensing or any refractive index changes. An example that this is a spectrum that we had. So we have a 3 LPG peaks. Let's focus on the third one. We characterize for temperature. We end up something like almost 6 nanometers of shift per degree Celsius, almost double when compared to common silica slopes or calibration curves. But the most interesting thing is when you compare the result for refractive index values, which are belong on the region of 1.48. In this region, because mostly of the refractive index of a Zipline as a material, which is around 1.51, we had a sensitivity of something like 1400, more than 1400 nanometer for refractive index unit, which is quite high for just an LPG without any other materials included around it. So more or less, this was a brief introduction of what we are doing in the company, what we did, some of the topics that we did. We are a company that have an expertise on the development of this kind of gradings. And we have some experience of, let's say, 6 years on these exotic materials. And to answer the question that Antonio possibly will ask me in a while, what can you do? I just answer, what can they do for you? We think that it will be fruitful for us to find strategic partners and or collaborators, help us to commercialize in the future this technology, and work together to improve these components for future high-power mid-IR fiber lasers. So that's all from me. Thank you for your attention. And if you have any question, I will try my best to answer.
Good, Andreas. Thank you very much for the presentation. So as I mentioned before, we have time for questions. So raise your hand and you can make your question directly to Andreas.
Shall I remove it? I am sharing
That's
now.
okay. Yeah, Pierre.
Hello, Andreas. Thanks for your nice talk. I wondered if you have presented examples in the low end of the middle wave infrared spectrum, 2 micron, 3 micron. Are you seeking application at longer wavelengths, 4, 5 microns, and so on? And do you think fiber laser, for example, could be possible at these wavelengths?
Usually Z-plan is going up to 4.2, something like that wavelength. That's the maximum. What we achieve and at lower wavelengths is also applicable, easier also for the full spectrum of operational spectrum of this fiber. So it's possible. The problem that we have now is we don't have a characterization set up to push, let's say the component is this wavelength. But we strongly believe that what I show today is repeatable also to higher wavelengths. I'm not sure about chalcogenide fibers, didn't work. I mean, to extend this application to more than 4.2 microns, but at least for the indium fluoride and Z-plan fibers, yes, we are confident that we can work with these wavelengths.
Thank you.
Any other question or comment? I have a question regarding the LPGs gratings. You mentioned the application in measuring liquids. Do you see potential for humidity measurement, or is other type of measurements what they could be used for?
Basically, we characterize these long period gratings in 4 regions. One of the refractive index regions, one of them, it was close to 1.33, which is basically the water refractive index values. At this wavelength, we didn't observe any advantage compared to silica. I mean, their performance, it was similar. Maybe at 3 point something, or if we make the grading at an absorption band, and a wavelength that we have a water absorption band, for sure the sensitivity will be much higher. But at this, let's say, neutral refractive index region, a wavelength that we test, the highest potential, it was in 1.48. It's basically liquids and this kind of.
Okay. Now, I was thinking if you tested the detection of a small amounts of liquids, or for the moment, you know that there is some response there. So you have the general idea that it can be used for this application, right?
Yes.
You don't have experience with the on-field measurements yet.
No.
Okay. And regarding the fibers for lasers, you mentioned that you studied fiber for continuous wave lasers. What about pulse lasers? Is something that is in your plan for the future? Sorry about this slide. That is.
Yes, it is something that we are working on with some optical fiber couplers, but it's quite challenging because our concept is to have everything in the fiber. So at the moment, some critical, let's say, components are missing from the market to be able. But let's say that we have some plans in mind which are still in very low TRL and maturity of technology direction. Yeah.
Very good. Good. So for all the laser companies here in the room, so feel free to discuss with Andreas your potential ideas, and probably they can move further. So Andreas, I think there is no more questions from the audience. So thank you for being here today, and thank you for your presentation.
You.
So we can move now to our next speaker. So we have Ross Stanley, is the CSO and partner of the company 4K MEMS, a Swiss company that they are making miniaturized light sources for different applications, machine vision, spectroscopy, and he's going to present today the broadband IR emitter chips. So Ross, the floor is yours. Thank you.
Okay. I hope you can see my screen.
Yeah, and we hear you well.
Okay. It's a pleasure to be here to present our broadband IR emitter chips. Just a little thing, we are 4K MEMS. We are based in Switzerland. We are a fabless business-to-business company developing novel MEMS emitters. And so what I want to show you today is what we call our thermal light emitting devices, our TLED. We call them that because they're very small and they resemble a lot what an actual LED looks like. This is a Eurocent, and this is one of our fully packaged chips. It's 1.4 times 1.4 millimeters in size. If we zoom in, we see our hot plate glowing brightly here. It's at 2100 Kelvin, sitting in a vacuum package. And we do all this, the packaging, the MEMS at a wafer scale. So this is a completed wafer. We're looking at the backside. These are the little chips which we can pop out and mount completely on a PCB. So how does this work? A standard thermal light source, MEMS thermal light source, basically has a high emissivity layer sitting on a suspended membrane, and there's generally a resistive heater on this membrane. This heater gets hot, and the high emissivity layer glows, and everything is very nice, but it generally works up to temperatures of about 1000 Kelvin. Our principle is different. We start with a continuous membrane, all of the same material. In this case, it's tungsten, and it's suspended by these resistive heater springs. We put current through the springs get very, very hot, and the heat is transmitted to the membrane, which then loses it through radiation. So the nice thing about this is we get a very uniform temperature of the membrane. And as we heat it up to 2000 Kelvin, the membrane gets bigger, and the springs allow this expansion by simple rotation. So this gives us a very stable plate. There's no buckling going on, very uniform temperature. Obviously, it needs a vacuum. We're making it this way. We have a through glass via where we bring the electricity up the MEMS there. We then have a capping layer with a getter, all under vacuum. We put this together on a wafer level process, and it turns into something like this. We've been working on it for a few years now. Back in 2021, we managed to get the MEMS devices working in a probe station. This gives us first light. It showed that our emitters were stable and bright. Then we moved to surface-mounted packages. These were very nice demonstrators, but they're very expensive and not scalable at all. So towards the end of last year, we managed our first chip-scale packaging. And what's really nice about this is we can move from dicing to PCB. This is one just simply soldered directly onto PCB. This one is on, this one is off. We can put them on flex. And as you see here, we just don't necessarily have one emitter. We can actually have 4 emitters here. So if we look at device characteristics, as you've seen, they're very small. The emitting diameter is about 160 to 30 microns. So we can have multiple emitters. They're very flat. The bowing is less than 5 microns. And they're very uniform, which means the temperature across these emitting areas is about plus or minus 5K. These characteristics make it really nice for optics because we have a flat, small emitting surface. We can even include micro lenses. As I'll show, they're relatively fast for thermal emitters. We have a broadband spectrum out to 5 microns. We are talking mid-IR here. And of course, there's a wide range of analysis, as we all know, for these wavelengths. I repeat, the fabrication is compatible with standard MEMS foundry process, and we have wafer level manufacturing packaging, so which means that at high volumes, we can make these guys really cheaply, which is really interesting for opening up consumer and eventually automotive markets. This is how the devices perform. This is showing what happens as we change temperature. Our voltage, the devices get very hot. We go up to about 3400 Kelvin. We generally operate at 2100 Kelvin, which is slightly below 1 volt. Here you can see the device glowing nicely, and this is the spectrum. This is with the glass window. It's peaking about 1.2. When you put a silicon window on, we get out a nice emission out to 5 microns. As I said, the devices are relatively fast. This is showing the on-off time measured with silicon detector in red and indium antinomide detector from Hamamatsu at 4.2 microns. So you can see the response time. And we compared this with the main competitors. We won't name them, obviously. And we see we're considerably faster. We have a 100 hertz 3 dB point. We said we could add optics to this, and this is very nice. We can put, if we put a silicon layer on top of it, due to the high refractive index, we can collect light with very high efficiency and then beam it using a filter, or sorry, we're using a lens. And micro lenses can be made on wafer scale, so can filters. So we decided to show what we could do this with a project organized on the fabulous pilot line. Focuslight made the micro lenses, Viavi made the pixelated filters, CSCM blew them in place and measured them. We made and test the system. So what we have here is we have our emitters, this silicon chip on top of it with our 4.2 micron filter micro lenses and the 3.585 micro lenses, filter and lenses. So if we're going to do gas sensing, which we're interested in, generally what one does is has a broadband emitter, and we have two detectors where we have a on-band and off-band filter for the gas absorption. This is pretty standard. It assumes that the changes in detector response is less than change of how the emitter ages. But because we're very hot and because we can integrate things onto detectors, we thought we would do things differently. So we got our module with our two emitters and we put a single silicon detector behind it. And now we can take the ratio of these two emitters without the filter, using basically stray light on the silicon detector. And because silicon is so sensitive, we don't need much light to get this done. And then we do time division multiplexing. We turn one on and one off, and then look at what's happening on the detector. We set this up with the standard 40 millimeter path length reflector to concentrate the light. We use a piezoelectric detector with no filter onto it. And we simply stuck the silicon photodiode here. It's just taking light leaking out from the side, which works well because silicon is so sensitive. So what we get is we have our two emitters. So we have the signal coming from a reference emitter measured by silicon and the IR signal coming from the reference emitter. And then we can compare that with the signal coming from the device, which is at 4.2 microns. And so what we see here, over time, we have a chamber where the CO2 concentration is changing. We can then back calibrate that because we took the chamber and we put two Sensorion detectors into it to give us a background signal. We looked how the CO2 changes in time. We can use that as a calibration curve. We can compare it with our emitters, and then we can look at the residuals. And when we do that and we look at the difference between what we're getting from the Sensorion, albeit photoacoustic detectors, we see a very similar response. So we can get down to the 10 to 20 ppm range. What's interesting about this concept is that we are removing one detector and we're making our cheap emitters and filters together. We went one stage further. We decided what can we do with a really, really small emitter? And we said we can make a really, really small NDIR gas sensor. So we call it the 4K pill. This is here. This is in comparison to the smallest commercial NDIR sensor we could find on the market. Inside is our emitter, two detectors, two filters, readout electronics. And we get performance similar to standard NDIR systems. We can even extend this within the same form factor to multiple gases with minor increase in size. The design inside, I can't show you its unique optical design. We're actually submitting the patent on it tomorrow. But our goal was to show something which looked small enough to go into a smartphone, because people are interested in analyzing glasses around us when we're sleeping, for example. And so it's interesting to be able to go towards this. We have a single device. This is what we make. We're trying to address different markets, from illumination systems, embedded spectroscopic, to gas sensors, as I showed, and calibration sources. So to summarize, we have these emitters, which are much smaller than everything else. We can integrate microlenses and filters. We're targeting high volume applications, not feasible using existing solutions. And to finish, we can supply broadband IR emitters for evaluation and test. And we're looking for partners in detectors, filters, and also for novel gas sensing applications. Thank you for your time.
Thank you very much, Ross. And thank you also for this summary of the questions as well. So we have time for questions. You can raise your hands. Somebody interested in supporting 4K MEMS in any of these topics? I have perhaps a question regarding the gas sensing, because you show the idea of the structure. Is something that you have already developed a kind of demonstrator, or is an idea of the system that you didn't yet test on which kind of bench? This one, this architecture.
Yeah, this architecture, these are results from testing this architecture. So
with another partner, or is that something that you develop inside for?
Oh, this is 100% internal. We developed all of this ourselves. We also developed all of this internally ourselves. What we notice is that our emitters are so much smaller than anybody else's. People are not really too sure how to use them. And so we got pushback from people saying they're not big enough and we don't get enough power from them. And we went around and said, if you do intelligent design, you can get the same results as from larger systems, and we can benefit from size.
Yeah, good point. So we have questions. Christoph from Photonics Innovation.
Quick question is whether you can shape the maximum intensity of your emitter. I've seen with silicon window, it's peaking around 2 microns. And if you can go faster than this 1 millisecond.
The 1 millisecond is really a question, or the 10 milliseconds is really a question of efficiency. If we make the devices more inefficient, we can make them faster. But that's a question of power usage. So if you don't mind wasting some power, we can modulate them faster. We've done tests up to 8K modulation for 3 dB, but they weren't the most. They were much smaller devices, and they weren't the most efficient. But if you can afford to lose the power, we can get up to those speeds. Your question on intensity on the wavelength, which direction did you want to move it in?
I would like to move to around 3 microns, 3.5. This is the maximum intensity or sensitivity of the indium arsenide detectors.
Okay, yeah, we can do that by cooling the device, but then we get less light out. And actually the efficiency goes down. It's just a question of temperature. We can't actually tune the emission itself because it's mainly black body emission. As you know, this is just temperature dependent. So we are involved in projects where we're operating those wavelengths, and it's not a real issue. It's always a question of how efficiently you use the light. And as I said, because we have nice flat emitters, if you do the optical design right, we can get very efficient use of light. If you're looking about beaming light a kilometer, you're better off with the laser. Does that answer your question?
Yes, that answers the question. I thought you have very good indium arsenide detectors. You will see them.
Great. Looking forward to it.
So David from MAPSI.
Hello, thank you very much for your very nice presentation. I think that you have a very good technology. And that's funny because the last time that we were in Barcelona, we were in the annual meeting of EPIC, we were looking some partners to place our filters on the top of their emitters. And here you are looking for some filters. Our technology is pure silicon. So maybe we should talk about it.
I would say absolutely.
So
David is
I
going
take
to be the
your
next speaker.
Okay.
So Ross, you can check his presentation as well. Any other question or comment for Ross? If not, thank you again. Yeah, we have final presentation. No, we have Robert Lytle from Fraunhofer.
Yeah,
Final question.
Yeah, just a question about sensitivity and also thermal issues. If you have that all small packaged, so you need a certain path length to register also small concentration changes or so, right? And it's rather that you can have a good selectivity to high concentrations, but if you have only a poor gas concentration, for instance, CO2 has 4% or so in the air, or and you want to see the level from 4 to 6%. It's difficult. When you have 100%, it's clear. Then you are very sensitive. How is about your sensitivity and also the thermal issues?
So in the end, we got within this tiny package, we're able to get, at least on paper, path lengths in excess of 40 millimeters, which is roughly the standard length you use in standard NDIR. So we can get to the 20 ppm. And the device we had wasn't optimum. We're only getting 50 ppm sensitivity. We see why that happened, and we believe we can get to 20 ppm without much of an issue in the same package size. Otherwise, as you say, it makes no sense. It's easy to have a small insensitive detector. The question is, can you get the same performance in a small package? We can, because we have a really unique design, optical design inside it, which makes the use of the tiny emitter. With regards to power consumption, it's basically the same. My apologies, I should have put up the specification sheet. Slap on the wrist. It's roughly about 100 milliwatt is how much the power we're using.
It was rather about the temperature during lifetime, or do you use it, have some milliwatts, okay, it heats up, and then you get some drift, perhaps. No drift. You are drift free.
We don't test in the lab. The DT is 0.1.
Okay.
Which means that if we go from roughly 0.1, if you go from 10 degrees to 100 degrees, it's going to move by 10 Kelvin. At 2100 Kelvin, that means the spectrum is unchanged.
Okay.
The devices are really, really, really stable.
Okay. Thanks.
You're welcome.
Good. So I think there is no more questions. So thank you again, Ross, for your nice presentation today. And it's a pleasure to introduce the next speaker, David Cardador from the company MAPSI in Sabadell, close to Barcelona. He already introduced himself that they do filters for sensing and imaging. Thank you, because you are traveling today. So thank you for the effort of being here and presenting your solutions.
Thank you for allowing us to be here. I will show you our screen. Please tell me if you see it correctly. Yeah, do you see it properly?
It's not in full screen, but...
No, I'm doing it right now.
Okay.
Okay.
Good. Thank you, David.
Thank you. So, well, yes, we are MAPSI. Well, I am David, the CEO of MAPSI Photonics, and we were started in 2021 in Barcelona with the goal of manufacturing and changing the way how infrared detection is done, specifically regarding infrared filters. But we also want to move to other components. But step by step, we firstly started with infrared filters and windows. We have a B2B model, and we are not a fabless. We manufacture because I just... No. We are not fabless. We have our own production plant, and this is why you can only see here the stairs in the picture, because we are the only ones who know how to do these the machines that we use to manufacture our filters, that are done with disruptive technology that I will explain a little bit later, that is called macroporous silicon. So everything, all those filters are done here in nearby Barcelona, and the design and everything is done by MAPSI. And we are focusing in industrial partnership, more specifically in process monitoring, gas detection, and surveillance of industrial plants. As I said, we give around to the technology that it's used commonly, the multi-layers. I don't know if you're aware of how multi-layers are done, but basically they are deposited one layer over another, and over a substrate that it's typically germanium or silicon or some chalcogenoid. And because of they want to target those filters, for example, for the gas detection in 4.2 like CO2, or in upper wavelengths like in the HF6, which is SF6, sorry, which is in 10.6 microns. The thickness of those layers have to be thicker, much more than in the visible or in the near infrared. So they have some delamination problems that in turns means that they have the filters, they experience low optical quality, low robustness, and they have to put some other like DLC, diamond-like coatings, in order to be more robust, etc. So it makes more expensive. All of this is given because they use these thick layers. And our proposal is based on just the opposite. We avoid the use of layers, thick layers or thin layers. In any case, we don't use them. And what we do is we perform some holes in a substrate in silicon. And by controlling the geometry of those holes, that means the length or the emitter of the holes and so on, we are much more robust because we are only using silicon. And also we can enhance the optical resolution and the optical response even more when we are in the long infrared region. Here we are very strong. And also, since we are using we are not depositing, so we are using a different process of manufacturing. It's based on a chemical process, so we save a lot. That means that we are a little bit more greener than the competence. And also everything done here as I was saying, in Barcelona, and we can somehow support the European sovereignty. So here are the products that we produce. You can see the narrow bandpass filters, the windows, and also neutral density filters. We are developing them. We are trying to miniaturize them as well, so they can be integrated in miniaturized detectors or emitters, like in the previous presentation. And we have tested them, all the characteristics, but here in MAPSI's dependencies, we saw that they can be cleaned either with water, alcohol, or dry wipes, and you don't lose any optical feature. Also, we support really well corrosion, and also we don't have a shift in our optical response in the windows part when you will have a change in temperature. And regarding the bandpass filters, we can see that we have a less wavelength shift depending on the angle of incidence, and also we experience a third part of the variation in the transmission because of this angular dependency than multi-layer filters. And everything, again, because we are not using those diffractive layers. So here are the questions that they told us to ask and to respond. So what can we do for you? We have a novel technology, so we can supply you with different filters that are very ad hoc, very customized to whatever you want to produce. We are really good in this ad hoc and customized design. For example, we have a new customer that they are doing a 3-band, so three different filters in the long infrared region, for example, and we are specialized and somehow in doing all these difficult things as well as the standardized one. And also we can do, if you need a double check, we can do for you some FTIR optical characterization. Another customer of us, they had they didn't realize that they had a problem in the filters until they double checked, for example, and they saw that the transmission that the supplier told them was 30% less than the one that they wanted. So maybe we can do this also for you if you have any problem with one of the filters. And what can you do for us? We have, as I told you, internally tested and characterized those filters, but we want to characterize them with a third parties. So if you have aging machines, or you can test the robustness, or even you want to test them for new applications, we are totally open, and here we are to hear your suggestions. And if you liked something or you want to ask something, here I am also. So thank you very much.
Thank you very much, David, for the presentation. So we already have a question from Mohammad, Radiometer Medical.
Yes. Hello, David. You mentioned something about angular dependence of less than 3%. Can you put a few more words to it? Is less than 3%?
Yeah, under a degree of
yes.
45 degrees.
Okay, so 45 degrees, less than 3% shift of the peak wavelengths, or yes. Great, thank you.
That depends on the design as well, but we can tune it.
Yes, thank you.
Ross?
Thanks, David, for the nice talk. And going back to the angular dependence, when that shifts, does the transmission drop, or does it stay constant?
Sorry, can you repeat, please?
Yeah, when you shift when you change the angle,
yep.
Does the transmission, I know the center stays the same, but does the transmission stay the same? The amount of light going through?
As I was saying, it just drops 1% in this expression that I was saying before, 45.
Yeah. Okay, and then the off band, how good a rejection are you having off band? Because that's really important if you want a good narrowband filter.
That depends. Now we are doing an OD3 in mid-infrared region and OD2 in the long infrared region.
Okay.
Also depends on the sensitivity of the detector. So in the long infrared region, they are not as sensitive as in the mid-infrared. So this is well.
Okay. Cool. Thanks.
Thank you.
I also have a question regarding the test that you mentioned in your last slide. When you talk about aging and roughness, does include the thermal measurements, UV for the aging, or must they be in a specific kind of test for your product?
Yeah, well, it has to be, for example, we are talking about temperature and humidity tests, for example, and how they evolve during all this exposure in these hard conditions, and all these that are set in the specs. I don't know how to say this in English, but well.
So somebody with a thermal chamber.
Sorry.
Somebody with a thermal chamber can do the job in terms of checking temperature and okay. Okay, because we have a few members that are offering services in terms of test. So I'm going to have a look and I will let you know if I find somebody that could be interesting for you.
Thank you very much.
We have more questions, Robert Fraunhofer.
Yes, so for instance, we are one of these candidates who could do aging tests. So we have climate chambers and also a stress or a shock equipment. So you can, within 5 seconds, or go from hot to cold. So also we have some mechanical robustness like chief clove testing, which aims a little bit the polishing with a clove. Yeah, could do set a number of runs and so on, and look for the stability. Two questions I had was, the one is about, is stray light an issue? And the second one, can you is your process that has this fidelity to make pixelated filters?
Potentially, for the second question, potentially we have this ability, but we have not tested them. So it would be nice if someone wants to try it with our filters. We can cut them, of course, but we cannot produce a miniaturized filter, not now, but this is one of the things that we want to do in the near future. And regarding the first one, you were saying about the straight light, right? You
Stray
mean
light, yeah.
to having a scattering in the central wavelength? We may have some kind of scattering, but we have controlled it very well, because it depends on it's called Mie scattering. So that depends on the wavelength and the shape of the hole. And if it's much less than the wavelength that you are targeting, of course, you are not going to have a lot of it.
So you would also have, of course, detection methods to detect. Not sure whether in the mid IR region, but for others wavelengths we have scattering detection methods. And what is the smallest size when you say, okay, pixelated is not possible? What's the smallest size where you say, okay, it's a homogeneous area of your filter?
Well, we have checked them in the CM. So the electronic microscope, and we have very good homogeneous. We are very homogeneous in in microns, but we cannot cut them in microns.
You cannot cut them. Okay.
Yeah.
Okay.
Because of the method of cutting, but they are very well organized in this size.
Okay, got it. Thank you.
Any other final question for David? If not, we thank you again for presentation today. Thank you very much for sharing your ideas and your challenges as well. Thank you, David.
Thank you.
And we can move to our next speaker. So we have a shorter presentation, a kind of one-slide presentation by the company Photonics in Poland. So it's a pleasure to introduce Krzysztof Kloss. He's going to talk a little bit about their indium arsenide mid-IR photodetectors. So Krzysztof, you can perhaps try to share your screen.
Yes, thank you, Antonio. Can you see my screen?
Yeah, we still have these black boxes issues.
Okay, I will move it away. Okay.
Now it's much better. Yeah.
Thank you very much for this opportunity to present our latest developments to Natasha and Antonio. Photonics is a small startup company which works on the core photonics and the emissivity growth of the 3-5 components with focus on the antimonides. My name is Krzysztof Kloss. I am founder of the Photonics and CEO. And in the past, I worked for the Vigo Photonics for 7 years. Then I moved to work for Huawei, Denselight, and also I was working as a consultant for AMS Osram. And for the last 5 years, I work on my own company, Photonics, where we grow 3.5 wafers for infrared detectors and lasers and LEDs. Today, here I would like to present some latest developments on the indium arsenide detectors, which were done, the development on the processing and passivation and characterization of our wafers were done in the cooperation with the Military University of Technology, Professor Rogalski and Professor Martyniuk group, who were worldwide expert on the infrared detectors. And our focus here are the indium arsenide antimonide phosphide compounds, which act as a barrier, and indium arsenide as an absorber material. Currently, we are limited to 2-inch wafer size. We work on increasing the wafer size. As the focus of the meeting is the media, I would like here to present the results of the characterization of our indium arsenide detectors. But maybe first I will go quickly and jump to some information about the problems with the indium arsenide detectors. This is the information from the Hamamatsu and Judson datasheets, and also from the latest publication of the Judson, which indicate that on the indium arsenide detectors, there is a problem that the detector resistance in comparison to series resistance are so small that actually in the room temperature unbiased operation, those detectors have a limited sensitivity in the center. Here you can see that in the center of the detector, depending on the temperature, the sensitivity can go 30–40% less than the maximum sensitivity. And here Hamamatsu and Judson are showing that by cooling down the detector, you can increase air shunt resistance of the detector, and then it gained a full responsivity in the center. And the big development of the 14 is that our detectors have such a good R0 or R shunt resistance that they work fine in the center for 1 millimeter size, even without cooling. I will show it a little bit later. And also, I will just highlight that it's very important the operation point of the detector. It makes a big importance, because if you bias the detector, you increase the flicker noise, and there are also some excess noise present, which are depending on the passivation, which strongly deteriorate the sensitivity or detectivity of the detectors. And this is usually not shown in the data sheets of the manufacturers, but users found out this when they try to use those detectors, that at low frequency, there are high flicker and excess noises, which makes it much more difficult to get a good responsivity. Here are the responsivity and the resistance of the detectors that Photon developed. And I would like to highlight here first the dynamic resistance versus voltage for the Photon wafer, which is here. And you can see that I extracted from the latest 2025 Judson publication characteristic of the dynamic resistance of their detector. And as you can see, at the zero bias, the detector resistance is just 30 ohms. And then as you bias the detector, the resistance goes higher and it's reach nice around 10K ohms. But as I indicated earlier, there are big benefits of working at zero bias, because then detector do not have a flicker or have a limited flicker noise and excess noises. And also these detectors which work in the mobile and handheld devices, where the current consumption is important, the low bias or zero bias operation is also important and convenient. So here you can see the results of the processing in 3 different fabs, which we gave 3 samples of our wafers. And as you can see, those detectors in around 1 millimeter diameter size, depending on the fabrication technology, they span from around 150 to 250 ohms. And this is big difference, because when we look on the data sheets of the Hamamatsu, Judson, and Vigo, this is the biggest 3 companies which manufacture this kind of detectors. For 1 millimeter diameter device, we can see that Judson offers 15 or up to 25, 30 ohms dynamic resistance, R0. Vigo offers around 50, 65 ohms resistance, and Hamamatsu similar 40, 70 ohms resistance of the detectors. And 14, when we measured this on a little bit larger masses, our detectors have around 200 ohms. And this makes them way easier to integrate with the preamplifiers, and these detectors have a good sensitivity. If we go here back and compare the responsivity characteristics of various manufacturers, the blue curve is measured for the 14, and this dip is because of the air, moisture in the air. We can see that the 14 detector is have a very wide spectral range and the highest responsivity at 2 microns because of a special design. And also it's relatively thin detector, so the maximum sensitivity is limited to around 0.8 amperes per watt. But as I highlighted here earlier, these detectors will not have such a problem with the drop of the responsivity in the center. In the real detector from Hamamatsu, Judson, or Vigo, you can expect that when you measure in the center responsivity at room temperature unbiased detector, you will see much smaller responsivity. Here we also added responsivity of the bigger detector from Oriba, 2 millimeter diameter size, and we can see it's on this size, the responsivity drops a lot. So just to highlight, the detectors we developed surprised many veterans of the field, and they have a very high R shunt or R0 resistance, which allows them to work at 0 bias with the full responsivity, and they have low flicker noise, no reduction of responsivity in the center, and very wide spectral range of operation. Here I would like to just highlight that this is the yield from one sample where around 50 dyes was processed, and we can see that almost 50% or 30% of the detectors have an excellent performance. Some detectors have a lower performance, similar or comparable to Hamamatsu, Judson, or Vigo R shunt resistance. But this kind of yield allows us to really look forward to deliver those devices on the market. The problem with probably with the Vigo, Hamamatsu, and Judson technology is that they use MBE. And in MBE, they used aluminum arsenide antimonide compound for the barriers, which give a valence barrier, which reduce sensitivity at 0. And probably there is some problems with the yield, maybe because of the oval defects or other defects, and those devices have a little bit lower performance. That's all from me, and I look forward to your questions.
Thank you, Christoph. So we have time for one question for Christoph. Yeah, Pierre.
Yes. Thank you for this interesting talk. I noticed that you also mentioned laser component indium arsenide detector in your presentation. I think there is one example for the 500 micron with
Yes.
diameter. So can you tell me what is your analysis on this detector? I think the serial the dynamic resistance seems to be okay, but let me know.
I am very familiar with the laser component specs because it was analyzed, and in the web blog post I've put more details. Laser components devices use similar technology to 14, but a little bit different device architecture, as I suspect. And that's why our detectors have a little bit higher air shunt resistance. But it's a comparable technology. Yes, laser components detectors are very good.
Thank you very
Almost
much.
as 14.
All right.
You see the 14 detectors have a little bit larger responsivity at 2 microns, and probably this gap will widen, like we will have a better responsivity at shorter wavelengths. And your detectors have higher responsivity in the 3.5 microns range. And our detectors are have developments of the passivation technology that we developed together with the Military University of Technology, which are the subject of the NCBR grant, where we try an experiment on the passivation of the technology, because we found out, or we see that the good passivation is a key to have a good parameters at smaller dies and smaller chips, and also good passivation help with the flicker noise.
So thank you again, Christoph, for showing your capabilities, and anybody interested, you can reach Christoph and let me know, and I can introduce you to him. Thank you for being here this afternoon. And we can move to our next speaker. So it's a pleasure to have here Peter Totrup, the CEO of the company Eldir in Denmark. This company is developing a spectrometer for very dark samples, also low concentrations, and he's going to present fast mid-IR spectroscopy. So Peter, the floor is yours.
Thank you, and thank you for the opportunity to talk about our fast mid-infrared spectroscopy. So we are a company located in...
I also see some black, like black square somewhere on the bottom and the top.
I don't have that here. So maybe it's from the prior.
Can you try again? So sorry for the inconvenience.
What do you say now?
Like there I see a black big square on the top. I don't know why.
Me too.
Yeah, I'll try to go out. See. It worked when we started. I don't see that black square here at all. Do you see it still?
Yeah, it's like a big black square on the upper part.
Yeah. But
Is there a window open somewhere?
No, there's no window open anywhere.
You can try the full screen again. Let's see what's going on.
Still have the issue?
Now there is not affecting the view, so I think we can try.
Let's do that.
Sorry,
Okay,
Peter.
No, it's okay. So I don't know what happened. We are located just outside Copenhagen. NLIR is a part of the Neonomic Photonic group. 11 companies that's doing a lot of spectroscopy. We are selling globally. We have distributors and resellers in all time zones. And what we do, what we have done, we bring this speed to the mid-infrared. We do it by cheating age a little. We take the mid-infrared light and we take the mid-infrared light through a cavity with a nonlinear crystal, and then it turns out to be Vision light that we use silicon sensors to detect. So basically, our core technology is changing the wavelength of the light at the speed of light, and then we use standard grading spectroscopy methods to detect the spectrum. So our spectrometers, which is the main product we have from 2 to 5, is very fast. They go from 400 to 100,000 hertz. And have a nice resolution for many purposes. So you get full spectra from 400 to 100,000 times per second. And here in the corner, you can see a signal that is 40 kilohertz, but it's measured 80,000 times, 80 kilohertz. So you can see every second spectra is blank. And we have no cooling. It's just room temperature. We have a airflow fluid, so we have a temperature controlled, stabilized, and no moving parts except for the fan. So over the years, we have developed a little broader portfolio. So we have the spectrometers. We do some bundles with the kilohertz ones. We have light sources. We also just do the conversion unit, sell that one to people if they already have some detectors or spectrometers. And then we complete the things with some reflection interfaces, touch interfaces, transmission, and close-up interfaces. We have some collimators and also fibers that we have. So all in all, in the mid-infrared now, we can do the same as people have done for years in the Vision. And it's real-time measurements that are the interest of us. I mean, inspection of coating on coils or inline inspection of optical coatings, industrial waste plastic sorting, inspection of foils during production, inspection of wafers, every single chip on the wafer or LEDs. So what you see is, again, a standard spectrum in the mid-infrared, but we can measure that very fast. And here is an example of some optical components with different coatings. So you can see it's in the screen there. This is like 200 revolvements per minute, so it's very fast. We have some customers that measure a single digit during production, 1 millisecond to 11 milliseconds for optical coatings. Of course, we have the reflection spectroscopy for plastics and surfaces of sheets with coatings and stuff like that, powder. We also have this focused reflection of small areas, less than a millimeter, where people have to measure every single chip. And we have, together with our sister company in the Neonomic group, also some HR probe where people look into their liquids of oils or alcohols and stuff like that. And we also do mid-infrared NDT, we OCT optical together with a company called Noblis, so you can look into the first millimeter of surface in the mid-infrared. So this is basically what we do. We bring speed to the mid-infrared. So this is what we've done over the years. So we can say, rephrase is what we did for you already. We brought the speed to 2 to 5. And what we're looking for now is also going out again. We had a prototype from 8 to 10, but we are looking for applications where the speed is of an essence in that range. So we bring speed to the mid-infrared. So thank you.
Thank you very much, Peter. Thank you for the summary of your offering. So we have again time for questions. Yeah, Andreas.
Yeah, thank you for the presentation. I want to ask you to comment a little bit about the resolution of your spectrometer. You said you have very good resolution, but how much is the resolution that you?
So the standard, the 400 hertz is 6 inverse centimeters or 6 nanometers. But we can also go, we have shown we can go below 1 inverse centimeter for when we do custom jobs. So it's the same, around 3 nanometers, 3 micrometers, it's the same in inverse and nanometers. So it's around 1 nanometer.
Okay.
But I mean, basically it's 6 when we, the major product we sell is 16 centimeters, 6 nanometers.
And with the best resolution, you can maintain also the same speed of measuring? Or?
Yes, actually. So we can, the 130 kilohertz, we do 2.5 inverse centimeters.
Mm-hmm. Okay, thank you.
And then you get the full 2 to 5 micrometer, almost 1800 pixels.
Okay, thank you very much.
Good.
We have another question, George from Itachi.
Yes, hi. Sorry without video, but hopefully you can hear me okay.
We can hear you.
You mentioned semiconductor wafer inspection as one application, one area of application. I think with the speed, that's interesting for inline inspection, of course. But what would be the specific use case or use cases? So what would you measure that other inline inspection tools currently do not detect?
So
what kind of defectivity or yeah, what's
what we have seen there is there's some of the coating layers. So that's what we've seen. And we also have customers working with something we can't talk about. So it's there is various applications in that space.
But what kind of materials? What kind of semiconductor material systems? Just maybe as a rough indication.
It's more in the coatings.
Okay. So we're not talking making logic memory or power devices or things like that. None of those, or potentially also.
Potentially also, yes.
Okay, maybe offline discussion for more specifics. Thank you. Mm-hmm.
Yeah, I think it makes sense to connect you, George, with Peter, and you can discuss more specifically.
Yeah, great. Thank you.
Yeah, thank you, George. Any other question or comment for Peter?
So if I should put a little top on this, I mean, so the 8 to 10 micrometer is a place where you normally have a lot of chemical reactions, bioreactors. They can wait for many minutes. So a lot of FTIR stuff is okay, but we are looking for applications where sub-second measurements are interested in that range.
We have another question, Bobby from Thor Labs.
Yeah, so hopefully you can hear me. I know my mic sometimes messes up. Excellent.
Working well.
So I was curious about phase information and whether or not this process is able to transmit phase information through it, or if that gets lost and it's just amplitude that we obtain on the other end.
I mean, I have to talk to my PhDs about phases. So I would say amplitude. It's very linear on the amplitude. But on the phase, I don't know the nonlinear Selmayr equations enough to know what's going on there.
Sure. Thanks.
And there was another question, but I think hand is done now. So I would like to thank to Peter, and I think it makes sense to connect you with a couple of the persons that made the questions so you can discuss more in detail in private. So thank you again for presenting your solutions today. Thank you, Peter.
Thank you.
And we can move to our next speaker. So it's a pleasure to have now Pierre Chassin, Senior Business Development Manager at the company Laser Components in the office in France. Most of you know Laser Components. They are manufacturer of different solutions, also distributor, and they cover LEDs, illumination, laser modules, detectors. And today Pierre is going to present the new uncooled parametric detector modules. So Pierre, thank you, and the floor is yours.
Hello, thank you. Let me share my screen first. And then now I need to... Can you see my screen?
I see a Laser Components slide, so I don't know if this is one or...
Well, yeah,
okay.
This is the first slide.
Okay,
the very
good then.
first. All right, okay. So thank you, EPIC, for the invitation to this talk about middle wave infrared technologies, and I will elaborate on laser component contribution to these technologies. And as you have said, I will focus my talk on new uncooled pyrometric detector modules for broadband mid-infrared spectroscopy. But first, before we go into the details of the product we have made, I would like to have a look at the various technologies available in the middle wave infrared. Famous graph which depicts the detectivity of various detectors. So it's a factor of merit for detectors. Yes. As a function of wavelengths, and the wavelengths of interest for in the frame of this talk is between 2 and 20 micron around. So there are different types of detector in this range. There are the quantum detectors, which have been mentioned already during this session. You have in-gas detectors for the Square band until 2.6 microns. You have indium arsenide, indium antimonide detectors for the band between 1 up to 5 microns. And also you have lead salt detector and lead selenium detectors that you can see here in red for the same wavelength bands, which is actually very important for gas analysis between 1 and 5 micron. And then for longer wavelengths, MCTs are very popular for measuring up to 15 micron and even 18 microns. So that's quantum sensing detectors, and those quantum sensing detectors actually have a high detectivity, but are limited in bandwidth to their area of excellence. So SWIR are the beginning of the 1 to 5 microns and so on. There are a second type of detector, DLA-TGS and LTO, pyrometric detectors. They are heat detectors, which are essentially broadband over the whole wavelength range, because they actually detect indirectly photons by the heat which is generated on an absorber. And you have also thermopile, which is a similar type of detector, which is also broadband. So these detectors have an advantage of the broadband operation, but clearly the detectivity is lower. On the other hand, for quantum detectors, most of the time you have to cool them pretty hard in order to obtain good detectivity. For example, MCTs have to be cooled up to minus 200 degrees. So all in all, there are pros and cons for various type of materials. And I would like to highlight two materials that I think are of key interest for middle wave infrared. The first one is a quantum detector which is lead salt, lead selenium. And why are lead salt detectors important? Because of the wavelength range between 1 and 5 micron, which covers key absorption bands of important gases, and also because there is room temperature operation. And room temperature operation is a key asset if you want, for example, to do portable devices. Also, the responsivity of lead salt detectors is quite high, 10 to the 11th joules at room temperature, and you can triple this detectivity if you cool it relatively smoothly at minus 50 degrees. So this technology has an outstanding price to performance ratio. And I wanted to underline that in the frame of this talk. Also, large area are possible, 10 by 10 millimeters. And we are one of the few manufacturers in the world able to deliver such kind of products. Now, the second technology I would like to highlight is pyroelectric detectors. And there are two pyroelectric crystals, DLATGS on one hand, which is the pyroelectric crystal which has the highest pyroelectric coefficient. However, there is a long list of drawbacks of DLATGS: temperature range, moisture sensitivity, linearity, which is not so nice, and dipoling effects that can affect the sensitivity of the crystal. Therefore, at least we privilege another crystal which has a lower pyroelectric coefficient, but which we process with what we call advanced ultra synth detectors. And as you can see, we reach a detectivity which is very near to the one you can get from DLATGS. And on the other hand, temperature range is much better. Moisture doesn't exist, moisture sensitivity. It is linear over 4 decades, and there is no dipoling. So therefore, we have produced new products with this material, which is called lithium tantalate pyroelectric. So a first detector we made is 2 by 2 millimeter square. It is ultra synth at 6 microns when compared to standard devices, which are 20 micrometers thick. It has a nanostructured metal black absorber, which is patented. The uniformity on the active area is pretty good, 10%. We have 4 decades of linearity, and there is a low temperature coefficient. So all in all, this allows us to do a very nice and easy to use detector module, large bandwidth, with the speed of this detector is typically in the kilohertz range, but 8 kilohertz is already a very good result. The D star is quite high for the this type of detector, and the noise equivalent power is also quite good. And we made a second type of second optimization of our readout electronic, low noise readout electronic, made with our partner company Wired Sense from Hamburg in Germany. We have a 50 kilohertz bandwidth and a smaller, a lower D star as a compromise for the larger bandwidth. So this is the first product we have released on LTO pyroelectric detectors. The second one is even more innovative. It is a quadrant photodiode, which sensitive area is 2 millimeter in diameter, and which has a 40 micron gap between the 4 different channels. So this type of detector enables a user to center a beam in the center of the sensitive area. The thickness of this detector is again front, we have an excellent uniformity that you can see on the on the graph on the right-hand side, where you can hardly see the difference between the 4 channels. And we have a bandwidth of 50 kilohertz again, and a D-star that is at the required level. And this very good level is due to our specific process of ultrasynth detector and metal black absorber. So application of this detector, we see it in real-time monitoring and also tool for laser development. So now to conclude, I would like to highlight one use case of this type of detectors, room temperature Fourier transform interferometer that we have built, and this work was published in Optics Express of December 2024. We have used one of our LTU detector, what we call PR number 1 or PR number 2, together with a compensated beam splitter from company Omega and a ceramic power-coated thermal source from company Infrasolid from Dresden, Germany. And the characteristic of this room temperature Fourier transform interferometer are pretty good. The spectral band is as large as from 1.6 to 31 micron with only one single detector. The resolution is below 1.5 centimeter -1 over the entire wavelength range. The signal to noise ratio is 23 dB. And last but not least, the power consumption is as low as 1.3 watts because none of the component is cooled. And therefore, you can think of using this concept for portable devices. So that is one example. I had a second example, but conscious of time, I think I will switch it I will go directly to the conclusion. Just to say that, first of all, I have highlighted to you the interest of Litsol Technologies for middle wave infrared, which is an excellent material for a very good price to performance ratio. Second, I have shown you a new process on pyroelectric lithium tantalate chips that enables us to produce new infrared modules. And those infrared modules are a key element for an easy implementation of Fourier transform interferometer, where today it's probably not used because of the complexity of the technology and also because of the cost of this technology for the everyday users. So, and last but not least, we mentioned a quadrant photodetector in the middle wave infrared, which is a very original detector, which will certainly drive new applications. And I'm at the end of the talk. Thank you very much for your attention. And I am looking forward to hearing your questions.
Thank you very much, Pierre, for the presentation. So we have time for questions. I can perhaps start with the EPIC question. So we ask to the speakers what can they do for the others, but also what can the others do for you? So how can the Photonics community collaborate with laser components?
I think the first thing is to find use cases for example, for the quad detector, because this is a pretty new detector, which is which looks for a new application. People would be interested to use it. And the other point is low cost uncooled Fourier transform interferometers. People wanting to work in this area are of great interest for laser components.
We have a question from Christophe.
One of the problems with the pyroelectric detectors, I'm not sure whether it was mentioned here, it's their sensitivity to vibrations. They are having those membranes and vibrations disturb them. Can you say something about this sensitivity?
Yes, you are right. It's definitely something you have to address when you're working with pyroelectric detectors. Most of the people who are used to work with those technology are able to deal with that, but you have to be careful in the development of those detectors in order to avoid ultrasonic additional ultrasonic noise, actually. And there are a certain number of development tricks to avoid that. That's all I can say. It's similar, and that's why it's difficult to replace one design by another. So if you want to work with, for example, LTO detectors, you cannot just replace an existing design that you have, for example, developed for the LATGS. I have had this issue with one of my customers.
Yes, I think the pyroelectric detectors are very, very nice technology. If it's not a vibration and the speed limitation is the speed, then they are excellent in this performance to price ratio. And if someone's application do not allow to use them, then photon detectors, semiconductor ones, are better technology.
Yes, and there are also, as I mentioned, if you want a broadband detector, pyroelectric have an interest. And as I said, the sensitivity to vibration is clear, but you can counter it to some extent.
Thank you for the explanation.
Good. So if there is no more questions, we thank again Pierre for the nice presentation today. Thank you for being here this afternoon with us.
Thank you.
And we can move to our last speaker. So we have Mathieu Carras, the CEO of the company Mirsense in France. Mirsense is a company with a lot of expertise in developing of quantum cascade lasers, also spectroscopy solutions. So Mathieu, the floor is yours.
Hello.
Hello.
Thank you, Antonio, for the opportunity to present the component we developed. So the talk is going to be mainly addressing the different components. And then at the end, I will open to the integration we do to make our own solutions for gas sensing. So we are a company which is based on quantum cascade laser solutions. So we are doing our own quantum cascade lasers. And as you know, quantum cascade lasers are mid-IR semiconductor lasers able to address the full mid-infrared range. So what we usually call the mid-infrared is for us 3 to 20. Everybody has this definition. I just stressed the 20 because, as you will see, with these lasers, and this is quite unique in the field of quantum cascade lasers, we are able to go up to 20 micron with our lasers. So we can really fully cover all this spectral range with our lasers. What you can address with these technologies, I mean, we all mentioned about gas sensing, so either air quality, worker safety, process control, greenhouse gases, but also we can go to more complex molecules like healthcare, like glucose, ethanol. And one of the main applications of these lasers today is to protect against missile with airborne protections. And these lasers are able to emit quite a lot of power, as you will see, in order to fulfill this application. So Mirsense in this field is basically as a unique low-cost technology able to follow on volume if necessary and can cover the broad spectral range even above 10 micron with innovative solutions. So we have 3 sites. One is in Orsay, where we do laser manufacturing, optical systems, electronics and software, and laser customer support. We have one new site in Grenoble where we manufacture our sensors, and I will show you the gas sensor we do with our lasers. And we do have a site in Montpellier for the physics modeling and the laser chip development. So basically, in terms of material, and this is what is a bit unique with our technology, is that we, of course, use the indium phosphide-based material to cover the 3 to 10 micron region with the QCLs. However, when we're going to go higher, we have to change the material, and then we go to antimonide-based material with, where we can go up to 20 microns. So substrate is indium arsenide, but on the top you have antimonide-based material, aluminum antimonide, indium arsenide. So with this super lattice, you can do quantum cascade lasers above 10 micron. So in the company, we are vertically integrated, as I said. So we go from the layer sequence modeling to the module delivery. So this is like a typical high heat load laser module, which can be either for high power application or for spectroscopy applications. We do have 2 clean rooms, one in Orsay, one in Grenoble right now. And as you see, all the lasers we do are done using MD, either on indium phosphide or on an indium arsenide substrate. Just mentioning that it's always nice to say we are ISO certified, not only 9001, but also 9100, which is higher class of certification. So if you want to have our components being used in aerospace or our modules, they are qualified for military and aerospace applications. Okay, so this is the first product line that we do have, which is the Power Mirror product line. It's basically a high power laser module. So you can have it either as a chip, as a module with a lens inside, with electronics, or even in a turnkey system. And very interesting is that the output beam of these lasers can be totally circular, and this is embedded in the chip. That means that it's very robust towards any vibration, thermal management issues, because this is the output beam of the chip, which is totally circular. And with this, we are able to have power above 1 watt at 4 micron, 4.6, and 9 micron, which are the main band of interest to go through the atmosphere. Typical beam divergence are in the 2.5 millirad region, which is suitable for a lot of application. Of course, we can do some beam shaping, change it for custom application, but this is the standard product. Just to give you an idea about the performances, the wall plug efficiency, as you know, quantum cascade lasers are the best in class in terms of wall plug efficiency. These are 2 graphs here to show to you why. On the left is for low power sources, so basically up to 250 milliwatts average power. In that case, we have wall plug efficiency above 15% in the low wavelength range, and around 7-8% in the long wavelength. This is direct conversion from electric to optical. There is all intermediate taken into account here. So it's really the full wall plug efficiency of the system. And when you go at higher power, and here, for instance, you see that we can reach above 3 watts of average power at 4.6. We still keep very high wall plug efficiency, close to 10 microns at 4 micron, above 15 at the 4.6, and in the 4 to 5 micron percent at the 9 micron. So that makes it very efficient sources. So you can use this wall plug efficiency either for extracting more heat or for making portable low energy application where you need mid-infrared. If I go to the second product line, which is the lasers for the gas sensing, housing is the same, because when you want to extract quite a lot of heat, of course, we can do custom packaging for people who want to have smaller, more cost-effective packaging. This is like more off-the-shelf package. In that case, we can go up to 17 micron. And in terms of product portfolio, we do propose pulsed operation QCL from 4 to 10 micron. There exists 4 to 10 micron continuous wave QCL on the market. So we are not competing with this one. There's a lot of offers for that. And then on the 10 to 20 micron, we can either offer CW or pulsed in the 10 to 17. Since we are the only one to be able to do that, we do CW. And above 17 micron, it's only pulse QCLs. Pulse means you have small pulses of a few hundreds of nanoseconds, for instance, with high rep rate. So it's quasi CW. It's not CW, but it's quasi CW. And we can go up to 20 micron. This is type of performance of the laser, threshold about 3.3 amps and powers couple of tenths of milliwatts. Okay, in terms of wall plug efficiency for DFB, so the laser for single frequency, we are talking about few percent. Of course, we can improve this one, but this is just the off-the-shelf components that we have. Couple of percent of wall plug efficiency, which is very high, as you can imagine, because if you compare it to a thermal source, this is all the power is inside less than a wave number. So all the power you need is exactly targeted your gas line. So it is very high brightness and very high power for high wall plug efficiency. These are examples of lasers at longer wavelengths, 18 microns, for instance, with continuous wave up to 18 microns. This is the world record that we have, and we can deliver such laser if necessary. Okay, and then as I said, we've put our own lasers into a gas sensor. And thanks to the pulse operation, we can do very efficient gas sensors, compact. This is a view of our gas sensor. It's like 10 centimeters by 10. It's like a cube of 10 centimeters of size. And this is and it's based on photoacoustics. So we don't use optical detectors as it was presented today, but we use microphone to make the gas sensing. You basically shine the gas with the laser. The gas is going to vibrate and create sound at the modulation frequency of the laser, and then you listen to the sound and you get a signal. And this allows us to go to ppb level sensitivity for most gases. The sensor is here. It's very easy to integrate. So you see the sensor, you see a suitcase, and a typical case you can put on your back. So it's rather small. Everything is inside. You just have to connect with Modbus, and you get the gas concentration from the system. So it's very robust for integration. You can have the ambient temperature ranging basically like from 0 to 50 degrees, no problem, because with this laser we can operate the laser at temperature as high as 60 degrees, no problem. This is a type of example of response. You don't see it's very, I mean, the accuracy is very good as well. You don't see the line which is the basically targeted concentration and the one which is the measured concentration. These are examples of molecules we do detect with our lasers, but of course we can do a lot of more of these ones. So all the gas line here exist at the laser level, and if there is an interest as well, we can develop sensors for markets that need such sensing technology. Okay, and that's the contact for these different components. So if you're interested in a laser, you can contact Adrien with our sales rep for the lasers, and you can contact Laurent with our sales director in charge of the sensor business as well for photoacoustic sensors for the gas you want to measure. Thanks for your time.
Thank you very much, Mathieu. Thank you for summarizing all your capabilities and for letting us know about this integrated solution. So Christophe, I have a question. Hello, Christophe.
A quick question. I've seen that these QCLs are developed on the indium arsenide substrate.
Yes, some of them. I mean, when it's above 10 micron, we use indium arsenide substrate. And when it's below 10 micron, we use indium phosphide substrate.
Oh, okay. That's very unique technology. Thank you.
Yeah, and we have demonstrated that if people want very large volume manufacturing of these lasers, we have demonstrated the capability to grow them on gallium arsenide and on silicon.
That's fantastic development. It's very difficult technology.
So it's done with the University of Montpellier in south of Paris. They have a very high-tech technology center for everything related to antimonide, as you may already be aware.
Eric Tournier, I know him. I track its development.
We have another question, Gassem from the National Research Council of Canada.
Yes, thank you for your nice presentation. For the system, for the gas sensing system, because it's used acoustic, is it the sensitivity could be affected by vibration? Because I was thinking that those kind of system can be installed on a drone or not.
In fact, of course, there is always a potential sensitivity to vibration because it's based on photoacoustics. But we managed to efficiently decouple the external vibration to the internal. So it's mostly vibration coming from the wiring. So I don't think there is any major issue of using it on a drone.
Great, thank you.
Any other question? I have a question regarding the measurement of the gas. I don't know if you mentioned if you need like a gas cell or a flow cell to make the measurement inside your system, or what's the method that you can do the gas measurement?
Okay, so in fact here there is the gas in and gas out. So you input your gas inside. There is a measurement chamber here, which is basically less than 1 centimeter cube, less than 1 milliliter. So it's very fast. You can go up as high as 1 liter per minute, and the response time can be from 100 milliseconds up to more than that if you want to integrate and go to low ppb sensitivity. So
do you need to control the temperature as well in this cell?
No, because the cell itself is stabilized inside. So basically, the gas is directly thermalized by the flow, which means that you don't need to stabilize your input gas temperature, except if the sampling method requires to bring the gas at a certain temperature because you don't want to have chemical changes. But there is for the measurement is not necessary.
Okay. Okay, very good. Thank you. Any final question for Mathieu? Well, if not, we thank you again for the nice presentation today. For showing
Thank you for the opportunity of
all your
presenting our
capabilities. Thank you, Mathieu.
Thank you.
As you can see in your screen now, we have the poll to rate the meeting today. So please give us your feedback so we can improve our next events and be more efficient. And we still have a couple of minutes. Just a final question for everybody, because we talked today a lot of about gas sensing. Some of you mentioned other applications. Peter mentioned about the coatings as well. So it's an open question about, do you think that there is what is needed to have more industrial applications for mid-IR apart from gas sensing? Is there something that is still blocking the technology from going to the industry? So I don't know if anybody have a thought about that. Yeah, Pierre, please.
Yes, as I mentioned in my talk, one of the issue, but for people who want, for example, to approach Fourier transform infrared spectroscopy is the cost. Actually, the cost of such kind of products is quite high and remains quite high. And the reason why is that detector all the key elements forming such kind of broadband spectroscopic instrument are quite expensive. And the key is to build lower cost room temperature devices. And we think at Laser Component that there is a lot of progress to be done so that we can bring these complex technologies and the ability to measure in the middle wave infrared range to potential users. There is one example, for example, pharmacists are still using chemical labs to analyze their onguent or their specific for their specific needs, and the spectroscopy could solve a lot of problem. It's just currently too expensive, and there are other very nice applications in the middle wave infrared. I could also speak about blood analysis and prevention in the medical domain. There is a lot of interest, and I think we need to make progress to bring our technologies to people who can afford it.
Yeah, Mathieu, any thought?
Yes, I just wanted to continue on what was just said. I mean, truly, the cost is a matter, and since we are doing gas sensing with lasers, people want to benefit from the sensitivity of applications like you mentioned, blood, but also gases. They want to go in the PPB, and there is this cost barrier. And cost sometimes is not only done in the components; it's also what's it's surrounding the components. So and just for this purpose in mere sense, that's why we moved to photoacoustics, because the detector was so cheap. As you said, we don't need to buy an expensive detector, but for the laser, we still have to deal with that. And so we also have to develop. Currently, we just develop an ASIC chip. So in order to do the full sensor with an ASIC, and this is something that matters because the electronics itself is sometimes more expensive than the components, especially when you want to do high resolution spectroscopy or such like that. So thinking about also what surrounds the component is certainly important, because you don't have access to modulators, insulator, all this, other components that are not the emitter and the receptor, but are, making life easier.
Yeah. Christoph, you also raise your hand.
One quick comment is that for now we developed indium arsenide detectors, but on the indium arsenide there are also sources developed, and there are on the market LEDs which are based on the indium arsenide antimonide phosphide. And I believe in future it might be that indium arsenide substrate might be a platform similar to indium phosphide, where you can develop integrated photonics with the sources and detectors and other components, perhaps, just like on the indium phosphide. It's just a matter of time and development of this technology.
I don't know, Peter, Ross, if you have any thought about or any comment. Also, of course, David and Andreas.
I think, again, price is an issue. I think as we go into the mid-infrared, we're always dominated by price. So getting the components down in price is important. There are other parts in the sort of the shorter part of the mid-IR. If we go sort of towards between 2 and 3, there's a lot of interesting things happening in wellness. But that's sort of at the edge. That's the shorter edge of mid-IR. I'm thinking about lactate and things like that, where there's potentially huge markets in the wellness and health sector. I'm thinking about 2.6 microns. That all again requires a hefty shift on pricing.
And what we encounter is also, I mean, the speed that we bring to the table is, I mean, still is niches here and there, but sometimes you just need the speed to solve these issues. And that's what we see, that then prices are not, of course, they are important, but it's more that solving the application.
Any thought, Andreas?
Yeah, I think more or less it's the same. At the moment, this mid-IR market is a little bit more expensive sport than the other wavelengths, but I think as the market is a little bit growing, the prices, I'm feeling that will drop down. At least from my case, the most expensive cost is coming on the characterization equipment, and source which is more higher. So considering this, the final product is also more increased in terms of price. But in my case, the prices can be reduced from a large volume manufacturing, because the cost is custom, let's say. It's not, yeah.
I'm thinking in the application Pierre mentioned in the pharma, will the demonstration in the lab be needed before going to inline measurements, for example? So the first way should be to go to laboratory people that they can test spectroscopy in their application, and once they are, well, they see the advantages, they can think in installing inline systems or online systems, or are they totally separated?
So the question is for who? For me?
Yeah, for everybody in general.
I think this definitely you need to test as the users and to demonstrate. And one of the challenge with fluid transform infrared spectroscopy is that you need also a library that is adapted to the need of the customers. There is a lot of software analysis that you have to put in place. But definitely what we see is that there is room for improvement and reduction of cost. And as you have mentioned, a component is not the only solution. There is also integration. There is the choice of material for the type of problems you want to solve. And there are many approaches. But the market will grow by bringing a new solution to people who are not used to deal with mid-infrared spectroscopy currently, but who could use it.
Yeah. Any other comment or thought also from anybody else in the audience? Yeah, Mathieu.
No, I just wanted to say that one of the major issues we have is the fragmentation also of the market, because in fact the mid-infrared is 3 to 20, which is a lot of wavelengths, a lot of stuff, and so on. At the end, it's a matricial thing, and when you are inside one of the box, there is not much left. So this fragmentation is a major issue, because you don't have one spot to pinpoint to. So when we say we do like QCLs, in fact we have to do maybe 10 different products to cover. It's not like one product. So mid-IR is very broad, and it's not like telecom with a unique wavelength. So that's one of the key challenge, I guess, is that it's a very big world, in fact.
Yeah. Good. So we are 5 minutes over the time. So thank you for these final thoughts, because it's always interesting to know, and also thinking in that gas sensing was like the common market in the presentations, and it's always good to understand who other industries can benefit, and with is needed to go in this direction. So thank you for your thoughts. Thank you for the presentations, all of you, Andreas, Ross, David, Christophe, Peter, Pierre, Mathieu, thank you for the time, and thank you to all our attendees for the nice discussion this afternoon. And see you in the next online meeting. Thank you, everybody.
Thank you.
Bye-bye.
Thank you.
Thank you very much. Bye now.
Thank you very much.
Thank you.